Let's construct these generalized projection operators for an example. We take for our group, we take D3, the symmetry group of an equilateral triangle. The group elements are the identity, the rotation in the other direction, 120 degrees, and 3 reflections, let's say sigma x, sigma y, and sigma z. So that's isomorphic to S3. Here are the cyclic permutations, and here the transpositions and the identity. And as representation here, we choose these O operators, these OG operators acting on, say, functions in the plane. If you evaluate the result at x, then this was just the function evaluated at G inverse times x. So the G here really, the group element, thought of as the symmetry transformation, say in terms of orthogonal 2x2 matrices acting on this vector x in R2 here. Okay, so this is our representation, our U, and now we can construct these generalized projection operators. S3 or D3 has 3 irreps. First one is the trivial representation. Let's call it gamma 1. And for the trivial representation, we can construct the generalized projection operator P1, upper index 1. And now d mu is 1, so j and k run just from 1 to 1. So we have P1, 1. Now we have here 1 over order of the group, that's 6. And the matrix elements of our representation matrices are just the trivial ones from the trivial representation. So what comes here is just a sum of all these operators OE, OC, OC bar, O sigma x, O sigma y, and O sigma z. Then there was another one-dimensional representation. That's the sign representation. Let's call it gamma 2. And if we construct the corresponding projection operators, or just one operator again, it's P2, 1, 1. Again, it's also one-dimensional, so we have a 1 over 6 factor here. And now what happened in the sign representation, let's just copy this and write the operators here. The only difference is that now the reflections come with a minus sign. So that's the next generalized projection operator. Now we also had a two-dimensional irrep. And these are the representation matrices here. So we can use the matrix elements in order to read off the coefficients for these generalized projection operators. And that's what they look like. So we have an upper index 3 here for gamma 3. That's what we call these that's what we call this two-dimensional irrep here. And now let's see what happened to the coefficients. So if we construct P3, 1, 1, we need the 1, 1 coefficient. So there's a 1 here, so the identity comes just with a prefactor 1. There's a minus 1 here. There's a minus 1 here, that goes here. Oh, sorry, no minus 1s, minus 1 halves, but that's what we have here. Here we have a minus 1 for sigma 1. That's just this minus sign here, and then there's a 1 half for sigma 2 and a 1 half for sigma 3. I called them sigma 1, 2, 3, and up here I called them sigma x, y, z, but never mind. Okay, when we want to construct P1, 2, recall that since we made this transition from the inverses to the Hermitian conjugates for the unitary irreps, the jk becomes a kj here. So we really need the elements in the first column and second row now. So there's a 0 here, that's why we see no OE showing up here, and there's also a 0 here, no sigma 1. And now we have this minus square root 3 over 2. That's this coefficient. Same one with a plus goes here in front of the OC bar. And here for the sigma 2 we have this one, and for the sigma 3 we have this one. And so on. So this is how we explicitly calculate these generalized projection operators.